Hi, this video is about heat exchanger. Heat exchanger has been used very widely, and for example, here you see a picture of this 1966 Maston radiator. So another example here, you have for example, hot water comes in, and if you want to warm up the air, right? And so you have cold air coming and going through this heat transfer between the hot water and cold air. So and the result is this air coming out is getting higher temperature, and the water, as a result, is gonna get colder because it's losing heat. So that's a heat exchanger. So when we people go see power plants, you will see a lot of heat exchangers. So now also, for example, your computer, your CPU has a heat fan, right? And that's heat exchange as well. Now let's talking about what is energy conservation and mass conservation for a device like a heat exchanger. Then let's go ahead and label on this. We call this M water, W for water, and 1, okay, mass flow rate coming. Then since there's another inlet, it's for air, we're gonna call MA for air for 1. Then at the outlet, the water come out is gonna be mass flow rate water 2. Then air coming out will be mass flow rate of air coming 2. And first, I want you to pay attention, like basically the water and air, they are absolutely isolated. They don't mix together in terms of mass. There's tons of heat transfer going on, but there's no mass mixing them together. So in terms of mass conservation, we're gonna have 2 separate mass conservation. For water, we'll say mass flow rate coming for the water is gonna be the same as mass flow rate coming out, right? That's reasonable. And for air will be the same thing. The mass flow rate coming in for the air is equal to the mass flow rate coming out for the air. So they are equal. So we could potentially get rid of the subscript, just say water, mass flow rate of water. This will be mass flow rate of the air. Okay, that's our mass conservation. How about energy conservation? Well, we know there's a lot of heat transfer between the water and the air, right? But if we were to looking at this two of them together in a box, we call this control volume. Then them together compare to with surrounding environment, then we're going to consider there's no heat transfer of this orange box with the surrounding environment. It's well insulated, despite there are a lot of heat transfer going on between them, but there's nothing going of this orange box with surrounding. Okay, so ready for the ready to discover the energy conservation. So we'll have this energy for all of them coming in is equal to energy flow rate coming out for all of them. So energy comes in, there are 2, right? One is from water, one is from air. They both carry out energy. So then we'll have Q Actually, why don't we start to make our assumption now, so we'll save up some of the... So we're going to assume this orange box with surrounding, there's no heat transfer. And there's also no work done, or work done to the system, work done by the system. So it's not generate any work or require any work. Then we'll also assume there's no kinetic energy change, and no potential energy change. So in that situation, when we look at that equation for our energy, we will have something like this. We'll have our mass flow rate of our water come in here times water enthalpy. So that's going to be our H water come in. Plus the second inlet will be our air, mass flow rate of air times enthalpy of the air come in. That's our H air inlet. That gonna be equal to our mass flow rate of water, those two the same because we proved it right here, times enthalpy of the water at the exit plus mass flow rate of air times enthalpy of the air coming out. Right? So we have this equation for our energy. That's our energy conservation equation for this particular heat transfer between water and air. Okay? So, and here is going to be our mass conservation for each individual substance for water and air individually. So that's it. In the next video, we're actually gonna go further and using an example to see how the heat exchange works. All right. Okay, see you next time. Bye.